Aló. Hola. Voy a hablar un poco en español, después en inglés. Gracias, Cristian, por la invitación, por el honor de estar acá, y por los colegas que están. Voy a tratar de hacer una rápida revisión de cosas que por suerte no se han hablado. Así que vamos a tratar de avanzar rápido, porque tengo demasiadas diapositivas. Vamos a ver cuál es la aproximación que yo utilizo para acercarme a la plasticidad fenotípica, ¿ya? Yo utilizo esta aproximación que se llama macrofisiología, ¿ya? El estudio de poblaciones a lo largo de un gradiente ambiental. ¿Por qué? Porque tenemos estas condiciones únicas a lo largo de la costa de Chile, cerca de 5.000 kilómetros de costa, donde tenemos gran cantidad de individuos y grandes poblaciones distribuidas de la misma especie a lo largo de este gradiente. Como ha mostrado anteriormente en las presentaciones de Bernardo, existen gradientes en temperatura y gradientes en otras variables ambientales. Entonces, estudiar estas poblaciones a lo largo del gradiente es, en este caso, la posibilidad de estudiar cómo la plasticidad fenotípica puede surgir y por qué surge en algunos lugares, ¿ya? Entonces, la aproximación es a través de estudios de poblaciones a lo largo de un gradiente ambiental, en este caso latitudinal, ¿ya? Bueno, básicamente lo que hago entonces es estudiar estas poblaciones a lo largo de un gradiente ambiental, donde tenemos un valor fenotípico acá, y en el ambiente nosotros vamos estudiando cómo los rasgos varían. En general, les voy a mostrar trabajos sobre rasgos fisiológicos. Les voy a explicar por qué al final de la explicación, de la presentación. Entonces, estudiamos rasgos fisiológicos y vemos cómo estos rasgos explican la variabilidad, o se pueden explicar por la variabilidad ambiental. ¿Cuáles son las herramientas que usamos? Esto es lo que se llama jardines comunes, que básicamente llevamos poblaciones de distintos sitios, esto es un ejemplo solamente, por ejemplo, a la misma temperatura en el laboratorio. Y esos jardines comunes entonces nos van a indicar si el componente de variabilidad es ambiental, genético o es un efecto entre los dos, ¿ya? Genético y ambiental, esto se llama interacción genótico-ambiente. Entonces, esa es una de las herramientas. Tomamos individuos de distintas poblaciones a lo largo de la costa de Chile y los llevamos al laboratorio, en las mismas condiciones, ¿ya? La otra herramienta que nos mostró Vargas anteriormente son trasplantes recíprocos. Entonces, tomamos individuos de poblaciones distintas y los trasplantamos viceversa, obviamente con sus controles, en ambos lugares, ¿ya? Y vemos cómo es la variabilidad de los rasgos de estos individuos en esos lugares y lo relacionamos con la variabilidad ambiental. Entonces acá, si yo trasplanto de A a B y no pasa nada, entonces el ambiente no participa, por lo tanto es genético el cambio. Si acá participa, el cambio ocurre, esto es plasticidad, por lo tanto hay un cambio ambiental, y si se cruzan las líneas, de nuevo tenemos interacción genótico-ambiente. Entonces, con estas dos herramientas, trasplantes y jardín común, nosotros podemos empezar un poco a desentrañar cómo es la variabilidad que encontramos en el fenotipo a lo largo de el ambiente, en este caso, latitud. Esto es muy importante, esta es la curva de desempeño térmico para cualquier individuo ectotermo. Ya, esta curva de desempeño térmico, aquí tenemos la temperatura corporal, que en el caso de un ectotermo es igual a la temperatura del ambiente. La temperatura del cuerpo es igual a la temperatura ambiental en un ectotermo. Y este es el desempeño. Y acá tenemos varias herramientas. Entonces, aquí nosotros vamos a tener un rango de temperatura, a temperaturas muy bajas vamos a tener una variabilidad que se llama, un valor que se llama el crítico mínimo temperatura crítica mínima, que es que es donde el desempeño es 0, y a temperatura máxima el crítico termal máximo, que es donde el desempeño también es 0. Y tenemos un óptimo, donde el desempeño es máximo. Esta curva de desempeño es clave para estudiar los individuos y cuál es su respuesta a la temperatura, y obviamente, dado el contexto de calentamiento global, es importante conocer esta curva en los individuos. ¿Cómo cambia esta curva? Bueno, hay varias hipótesis. Una de ellas es que dado el calentamiento global, se incrementa la media. Por lo tanto, la curva se desplaza de un lado hacia otro, pero se desplaza completa. Se desplaza al mínimo, se desplaza al máximo. ¿Ya? Lo otro que puede pasar también es que se incremente la varianza. ¿Qué quiere decir eso? Que tenemos una curva pequeña, pero tenemos una curva más grande. Por lo tanto, un ambiente más variable va a presentar una curva más amplia. ¿Ya? Esto está ocurriendo con el calentamiento global. No está incrementando solo la media, está incrementando también la varianza, es decir, la frecuencia de eventos extremos. Por lo tanto, sería esperado que también incremente la varianza de esta curva. Y el tercer escenario es que incremente en media y en varianza, ¿ya? Y esta curva se deforme, en definitiva. Entonces, conocer cómo son estas curvas, las poblaciones naturales, a lo largo de un gradiente ambiental, nos va a permitir, por lo menos, conocer cómo cambia esto en la naturaleza y proyectar un poco hacia el futuro. ¿Ya? Vamos a ver un poco de cómo esta característica que he mostrado anteriormente pueden variar a lo largo de gradientes ambientales, pero donde ocurre un quiebre, ¿ya? Donde cambian las estructuras comunitarias de la costa. Si estuvieron muy temprano, Bernardo mostró que hay quiebres muy importantes en la costa de Chile, y uno está alrededor de los 30 grados de latitud. ¿Ya? Entonces acá tenemos una provincia peruviana, un área intermedia y la provincia magallánica. En estos lugares ocurren quiebres, ¿ya? Biogeográficos, es decir, hay un cambio de las comunidades, en este caso marinas, a lo largo del gradiente ambiental. Uno a los 30 grados, más o menos, la zona de Talcaruca, y otro a lo largo de más o menos la zona de Chiloé. Esas son las provincias biogeográficas a lo largo de la costa de Chile. Entonces, uno de los trabajos que hicimos, justamente para evaluar a la costa chilena como un experimento natural, no solo de calentamiento, sino también de acidificación del océano, es ver en estos quiebres qué sucede tanto con la variabilidad ambiental como con los individuos que viven ahí, obviamente. Entonces, por ejemplo, aquí tenemos el quiebre entre el área peruviana y la área intermedia, que es la zona de Talcaruca. Aquí, por ejemplo, solo mostrar, esto lo mostró Bernardo, creo, tenemos una gran variabilidad en la saturación de aragonita, que es muy baja. Acá el PCO2, la cantidad de CO2 que existe, también tiene una amplia variabilidad. Y no tengo acá la temperatura, pero la temperatura, Bernardo lo reforzó, muestra un patrón de variabilidad muy alta en esa zona. Entonces, estudiamos esa zona. ¿Qué sucede con la plasticidad fenotípica ahí? ¿Qué sucede con las poblaciones que viven en esa zona y que viven a ambos lados de ese quiebre? Esa fue la idea que está detrás de este trabajo. Bueno, esto un poco para mostrar un dato que hay mucho más, pero esto es una zona de surgencias estacionales que provocan este quiebre. Una de las causas de este quiebre son estas urgencias. Y esto, fíjense que es la variación medido en tiempo con CIFER continuamente. Entonces podemos tener desde 7,2 hasta 8 en poco tiempo. La variabilidad, en este caso el pH y el sistema de carbonato del agua, es muy alta. Y lo mismo ocurre con la temperatura. Entonces tenemos en sí, justamente en esta zona, un ambiente muy variable. ¿Qué se espera en un ambiente muy variable? Que la plasticidad sea muy alta, que la plasticidad fenotípica sea muy alta. Voy a mostrar ejemplos solo con estas dos especies, Escurria viridula y Escurria cebrina, y al final voy a terminar con estas otras dos, que es Peromitilus purpuratus y el cangrejo. Por lo tanto, el nombre del título de la presentación no está bien, sino que es un camarón que se llama Veteus imaginatus, que habita en las pozas intermareales. ¿Qué sucede acá? Esta zona de quiebre, que está aquí, línea roja, viene una especie, ¿cierto?, desde el norte, que es Escurria viridula, que se está expandiendo hacia el sur. Ya pasó este quiebre, se está expandiendo hacia el sur, y la especie Escurria cebrina viene desde el sur, y este quiebre no lo puede traspasar, ¿ya? Este quiebre biogeográfico, como muchas otras especies. Este es un ejemplo. Queremos saber qué características fisiológicas tienen estos organismos que no les permite quebrar esta barrera, ¿ya? Esta barrera ambiental, que ya sabemos que en temperatura y en condiciones de características del agua son importantes. Entonces, lo primero que hacemos es medir las poblaciones en las distintas especies, virídula y severina, y lo que encontramos, acá tenemos el contenido de carbonato de calcio, acá está la longitud de la concha, y básicamente lo que se encuentra acá es que en la zona de Alcaruca, que es la que me interesa a mí, en este caso, virídula, fíjense que no se ve afectada, tiene un patrón bastante igual, y esa es la que logra pasar. Sin embargo, severina disminuye enormemente su cantidad de carbonato de calcio acá, ¿ya? Y su tamaño corporal, justo en la zona de quiebre. Y no es tan bajo, obviamente, no puede traspasar hacia esa zona. Son los sitios muestreos. Entonces, algo está sucediendo con esta especie en ese lugar que no les permite crecer, y aparte, como no crece, tiene muy poco carbonato de calcio en la concha. Les medimos esta curva de desempeño térmico, ¿se acuerdan que la mostré al principio? Y esta curva de desempeño térmico lo que muestra, básicamente, es que en este caso, escurre virídula, muestra que, bueno, la población del sur tiene un desempeño menor. Estos son latidos del corazón, que monitoreamos el corazón, son latidos por minuto. Hacemos un electrocardiograma a la lapa y le medimos los latidos por minuto, y en este caso lo medimos a lo largo de un gradiente ambiental desde menos 1 a 38 grados, o menos 2, y lo que observamos es que las que están hacia el sur, en el curva virídula, se están aclimatando al sur, o sea, en el sur están funcionando mejor. Y en el norte, las especies que están viviendo hacia el norte tienen un desempeño mayor a alta temperatura. Entonces, existe lo que podríamos decir una adaptación a las temperaturas del ambiente local, ¿ya? Está ocurriendo naturalmente. Sin embargo, cuando vamos a esta que no logra pasar, la curva severina, fíjense que, a pesar de que se nos arranca aquí en los muelles, en Talcaruca, esta especie, no se ve muy bien acá, pero básicamente aquí sí. Aquí están los parámetros de esa curva, ¿ya? Esa curva es básicamente como nosotros encontramos una serie de parámetros que yo les había contado. Básicamente en la localidad de Talcaruca, fíjense que, por ejemplo, el CD max, que es la temperatura máxima, es 36 grados, la temperatura óptima es 31, tienen una amplitud térmica de alrededor de 29, y esta especie entonces, de alguna manera, a pesar de tener una amplitud similar a la otra, no puede traspasar este quiebre, porque básicamente no presenta una aclimatación a este ambiente variable, cosa que sí ocurre en la otra especie. Fíjense, por ejemplo, en el óptimo. El óptimo, el desempeño máximo que tiene este individuo, es 28 grados muy al norte, la temperatura más alta. Sin embargo, al sur, 23 grados, es decir, va descendiendo con la temperatura. Entonces, hay una adaptación al ambiente a lo largo del gradiente ambiental, lo que no ocurre en Severina. Por algún motivo no lo sabemos. ¿Ya? Estudiamos este mismo individuo, o sea, esta otra especie, en este caso un crustáceo, como les dije, un crustáceo que vive en pozas intermareales. Son bien famosos estos individuos porque es un sonido muy grande en el intermareal, ¿verdad? Los chasqueadores, snapping shrimp se llaman. Y aquí está de nuevo, pero aquí estudiamos 8 poblaciones, 7, disculpen, desde la provincia peruviana hasta la provincia malayánica. Y aquí lo que tenemos, básicamente lo que está mostrado acá, es la temperatura superficial del mar, y lo que está acá son la mínima y la máxima. Y lo que quiero mostrar acá es que en Talcaruca, donde está el quiebre, hay una amplitud térmica, una variabilidad mucho mayor. Y en la zona de Chiloé, en Valdivia y Chiloé, también se produce, no está claro dónde está ese quiebre geográfico, también existe una amplitud térmica mucho mayor. Entonces, la hipótesis que tenemos es que la plasticidad debe ser mayor acá, termal. Estudiamos a estos individuos y básicamente, esto no está bien. Discúlpenme. Básicamente lo que... No está. ¿Qué pasó acá? Se configuró. Pero básicamente lo que... Y tienen que creerme ahora. Está publicado, les puedo enviar el paper. Es que en la zona de quiebre biogeográfico, la amplitud térmica de este individuo es mayor. Por lo tanto, tiene una amplitud térmica y una plasticidad mucho mayor comparado con las otras poblaciones. Y lo importante acá es que esta población que está al norte de este quiebre y las que están al sur de este quiebre, independiente de que están al norte o al sur, esta presenta mayor plasticidad por el hecho de estar en un ambiente muy variable, es decir, la variabilidad de este quiebre biogeográfico es más relevante que la latitud. ¿Ya? Esa es la idea de esto. Y eso lo vimos con una serie de factores donde nosotros somos capaces de estimar la plasticidad. Lo estimamos tanto para la curva de desempeño térmico como para la tasa metabólica. Hicimos algunos mesocomos experimentales, ¿se acuerdan? Con sebrina y escurria viridula, disculpen, está mala la foto acá, esta es escurria viridula, esta es la población de Alcaluca, esta es una población más al sur, y básicamente aquí tenemos tres escenarios ya de acidificación del océano, esta es una concentración normal, y estos son escenarios acidificados, y lo que se observa acá, fíjense, es que a pesar de que colapsa, estas son normas de reacción, a pesar de que colapsa más o menos similar, la población que habita este quiebre biogeográfico, que en este caso es Talcaluca, siempre presenta mayor variabilidad comparado con la población más al sur. Entonces, existe una variabilidad en la respuesta fisiológica, en este caso la tasa metabólica. Si vamos a la otra especie, miren la variabilidad de esta especie, justamente en la zona, y esta es la zona más al sur. Y esta es la especie que no puede pasar. Fíjese el coeficiente de variación en este caso en la tasa metabólica, 34%, en la tasa metabólica acá 40% en la zona también del quiebre biogeográfico. Voy a mostrar muy rápido un trasplante recíproco, que es entre la zona de las Cruces y la zona del sur de Chile, Calfuco. Y este trasplante lo hicimos con la especie Perimulvirus purpuratus, un metílido. Y básicamente lo que tienen acá son la temperatura superficial del mar, salinidad, pH, ¿ya? La alcalinidad, la concentración de CO2 y la saturación de la guanita. Y lo que se muestra, para resumirle esto, acá está lo mismo, información, acá está en los meses, acá están las medias y las progresiones y su mínimo máximo, es que el lugar en el sur de Chile muestra una variabilidad mucho mayor que la localidad en Chile central, que en este caso es Las Cruces. ¿Ya? Y estas son las poblaciones: central, Las Cruces, sur de Chile, Calfuco. Y estas son una serie de respuestas fisiológicas: consumo de oxígeno, tasa de crecimiento, calcificación y la cantidad de materia orgánica que tiene la concha, que es una respuesta muy importante para efectos de gasificación del océano. Y básicamente lo que encontramos es que siempre la población del sur es más plástica que la población de la zona central. Es decir, vivir en un ambiente variable, donde varían muchas variables ambientales, que no sabemos cuál causa la plasticidad, no sabemos cuál es la que la ocasiona. Alguna de estas, puede ser temperatura, puede ser los parámetros del sistema carbonato, o puede ser la salinidad, provoca que los organismos en sus tasas fisiológicas presenten una alta variabilidad, ¿ya? Comparado con la población, en este caso, de Chile central. Y eso se puede medir con un índice de plasticidad como porcentaje de cambio, y fíjense, siempre la población del sur llega incluso, en algunos, como esta la tasa de crecimiento, a un 70% de cambio altamente plástica comparado con la población de la zona central, que básicamente presenta plasticidad baja. Conclusiones. Bueno, existe una alta variabilidad geográfica en respuesta a la variabilidad natural, más que acidificación del océano, del sistema carbonato de la costa de Chile. Y la temperatura. En todas las especies que hemos estudiado, moluscos y crustáceos. Yo solo estoy mostrando algunos ejemplos, pero créanme que estamos estudiando chitones, que son otras especies de moluscos, y hemos estudiado petroliste y ciprograpso, otras especies de crustáceos. Y en todas existe un patrón similar. La capacidad de aclimatación que tienen estos individuos varía entre las poblaciones, y el entendimiento de esta capacidad de alimentación es crítica para predecir las consecuencias de la circulación del océano y el calentamiento del océano a lo largo de la costa de Chile. Y, más importante, estamos casi seguros que la plasticidad en rasgos fisiológicos al menos a lo largo de los quiebres geográficos y en esos sectores es mayor comparado con las poblaciones que no están en este ambiente variable. Entonces, nosotros tenemos que nuestro cambio global, cambio climático, pérdida de hábitat, contaminación, y tenemos acá lo que se denomina ecología fisiológica, que es lo que hago yo, ¿ya? Entonces, la ecología fisiológica nos permite, a través de una serie de medidas, metabolismo, crecimiento, conducta, incluso reproducción, entender la ecología y la evolución de esta biodiversidad que hemos tenido. Entonces, y que tenemos. Entonces, esta ventana es muy importante para predecir los cambios que tenemos hoy en día. ¿Ya? Muchas gracias.
Tenemos tiempo para preguntas. Por supuesto. Ustedes pueden preguntar en español, ¿verdad? Allá hay una.
Poder regresar a la imagen de donde dice pH, de las primeras pH, mencionabas que son lucíferos. Y es que en relación hay unos valores que mostraban que decían 7.2. Hay un río ahí. No, porque se ve lo opuesto a baja temperatura como para pensar que es suficiencia. Entonces, será algo diferente.
No, no hay río. Esta es la zona que mostró Bernardo. De hecho, la zona de Tongoy. Hay varias cosas. Hay una fuerte surgencia, primero que nada. Segundo, lo que tuvimos acá fue un maremoto que está registrado justamente acá. Se me había olvidado. ¿Sí? Y ese maremoto causó algo en la bahía de Tongoy, que no lo sabemos, se lo suspendió, hubo de alguna manera ¿cómo se llama? Mayor materia orgánica, por lo tanto tuvo después mayor se resuspendió el material y esto afectó claramente la conexión. No tenemos claro qué es lo que pasó, pero lo que está acá es el maremoto. Así que tenemos registrado por primera vez un maremoto con un cifre. Por eso es ese tema. Pero sin embargo acá no. Acá ya tenemos una condición normal y igual alcanza esos valores. O sea, cuando la surgencia, que es muy fuerte en este lugar, está activa, puede llegar hasta 7. De hecho, se ha registrado. Porque estos son los primeros datos, Bernardo después siguió registrando en el tiempo y hemos visto una variación muy amplia en la zona. Pero sí, pudo haber puesto un círculo ahí con maremoto, por tsunami.
Any other question? No? Okay, thank you, Marco. Well, according to the program, so I want to introduce the next speaker. Is Juan Diego Gaetan. Juan Diego Gaetan is a researcher from the University of Hong Kong. In Hong Kong, he's going to talk about the phenotypic plasticity and active evolution in changing ocean.
Bueno, primero voy a hablar también, la charla va a ser en Spanglish, básicamente porque está Sania, hay algunas personas también que están viendo la charla a nivel pues, mundial, lo cual es súper bueno, gracias por facilitar esto. Pero básicamente la charla va a mostrar algunas ideas como cómo podemos integrar diferentes enfoques en ecología, biología evolutiva, oceanografía y biología del cambio climático, para entender un poco el potencial evolutivo de las especies marinas en respuesta a estresores ambientales y a cambio climático en sí. Yo sé que son muy buenos en la Universidad de Hong Kong, en la Universidad de Concepción, para la parte de oceanografía, entonces como que esta charla viene un poco más enfocada desde otro punto de vista que es mucho más ecológico evolutivo. So I really would like to start this basically talking about natural populations, and we have seen some examples before about the different approaches that we can use for understanding differences in the populations. And one of the things that I really want to highlight is every time that we think about populations, natural populations and species, we need to think about variability, in particular variability in terms of phenotypic variation. And we can get phenotypic variation in things like morphology, in things like physiology, life history, and even behavior. So all of this phenotypic variation usually is the result of complex interactions between genetic components like addictive genetic variants, the interaction of genes like dominance and epistasis, pleiotropy, and also genetic influences from the maternal background, but also for the interactions of environmental factors like epigenetic factors, and as well as the natural environment of the species and populations. And these interactions can change across space and time, and because of that, we can get different phenotypic responses in natural populations. So usually in climate change biology, we think about the species as the unit of like our model study, but we need to think more about natural populations and the difference among populations to understand more about the adaptive potential of species to climate change. And the thing also here is that if we just look at the distribution of the species, we can see that they change not just in the phenotypes, but also in the genetic background. And in most of these cases, the environmental factors are quite important, basically because the genetic components could be homogenized across populations, basically through gene flow and so on. So in some degree, the amount of environmental variability is quite important for influencing these differences among populations. And if we start talking about environmental variability, and especially for people working on oceanography, you will see that there is quite like an intrinsic characteristic of nature. You will see natural variability in temperature, in UV, photoperiod, salinity, pH across the globe. And this variability is quite important for marine species, basically because it influences not just the ecology of the species and populations through changes in the distribution of the species or the organisms, but also phenology, the physiology, and the interaction of the species. But at the end, it has an important influence on the evolution of the organisms, and this is the link that I'm going to try to address today. But as most of the speakers before trying to highlight here is that the influence of environmental variability is quite context dependent. So if you just look across the species distribution, you will see that environmental variability is quite different. And this is just an example here of global trends in temperature. You have minimum, maximum across the planet, and you will see based on that there are some regions that tend to be more stable in this variability, like in the tropics, and regions that, like here at the south, are more variable. And this is quite important because the context-dependent effect of this variability influences the tolerance and the physiological responses of the organisms to these local conditions. In more stable environments, you will see like a narrow tolerance and lower tolerance to variability in population and organisms. And in more variable environments with seasonality, you will see higher tolerance and you can predict higher plasticity. We saw some examples before with Mark. And if you look at the literature, you will see that this is kind of connected to something that is called the climate variability hypothesis. But in other fields, like in forestry, you will see things like specialization hypothesis and so on. So it's quite well documented in the science. And this is an idea or an example how to use context-dependent influence of environmental variability. This is a work that we developed with Marco in some petrolistas here in Chile, and natural variability across the latitudinal gradient in Chile, with regions that tend to be warmer and regions that are cooler, but also differentiate the amount of variability across this region. And it was important here because we can see that this variability influences differences in the thermal performance of the organisms. You saw the thermal performance curve before, and these differences could be connected to, in some degree, with different models of thermal evolution. Like in this case, the hotter is better, and also signals of local adaptation. Like organisms and populations in lower latitudes, they tend to show higher thermal performance, or T optimums, and organisms in higher latitudes, they decrease the performance, especially in terms of physiology. Now, if we think about CO2, pH, we can go to a upwelling system in California, the upwelling system here in South America. We will see how spatial changes in pH and also temporal changes in pH here in California, as well in Chile. All of these, like context-dependent influences in environmental variability of these factors, can influence, in some cases, like physiological responses and tolerance of, in this case, assertion, in terms of the capacity to cope with ocean acidification, and also to coronal algae in terms of the divergence of local adaptation and physiological plasticity. So the degree of the amount of environmental variability across the species distribution can shape the history, the ecology, and the capacity for being plastic in these organisms. So we have used these kind of ideas about context-dependent effects of environmental variability to propose that if we study the past and the present influence of this environmental variability, we can predict the potential for evolutionary responses to the future. And we can use, for instance, upwelling systems across the globe to create these ideas about how species can respond in terms of the genetic correlations and the genetic architecture of different traits, and how the fitness of these populations could change in terms of the future, especially in terms of ocean acidification. But what I would like to highlight is that environmental variability is not only important for these macroorganisms, it's also important for small organisms like phytoplankton, bacteria, and so on. And this is just an example of a work that we are doing in collaboration with Fieldboy and Cristian here in Tasmania. So we were looking at the Southern Ocean and how natural variability in sea surface temperature, salinity, nutrients, iron, and also seasonality creates this kind of fronts, different water masses here. But what is really cool is that these differences in variability also create some divergence, phenotypic divergence in a single species, in Amelia and Huxley. You will see some organisms that are heavy calcified here in coastal regions that are very variable, and organisms that tend to be, or morphotypes that are like naked, less calcified in regions that are more stable. But what is even cooler is that if you just look at the capacity of these organisms in terms of tolerance to cope with ocean acidification and the stress, you will see that organisms in variable conditions, heavy calcified, they are less affected, more tolerant to changes in the PCO2 and pH. And organisms that are in more stable environments, they are more affected, more highly sensitive to increases in the PCO2 and pH, and decreasing pH. So that's kind of connected with the idea of how context-dependent differences in environmental variability influences the tolerance and the capacity of these organisms to cope with ocean acidification. That's phytoplankton. We can even look at smaller things, and this is an experiment that was led by Johnny Stark in the Australian Antarctic Division. So we went to Antarctica, to the Australian base, and basically it was a huge experiment of natural ocean acidification. So with this beautiful system to induce changes in the water chemistry under the ice, and we basically were looking at changes in the community of bacteria across the benthic core. And what is really cool is that this system is quite stable. So the Antarctica is one of the most thermally stable environments on Earth. But the CO2 is highly associated as well with low temperatures. So any changes in the variability in CO2 could be an important driver of community changes. And that's something that we saw here, basically looking at not just the identification of the species of bacteria that change across the benthic gradient here, and also in response to ocean acidification, but also the function of these communities. So if we just think about how ocean acidification and variability in ocean, in pH and PCO2 could affect communities, we just need to think also that in one way it affects the structure of the community, but also in other way it will affect the function of that community. So basically I want to go back again to one of the first slides that is basically showing that environmental variability could play a huge role in the ecology and evolution of the organisms. So in the work that I have been doing in the last 5 years, I'm trying to use this idea of climate variability basically because if you start understanding the effects of context dependency and climate variability, you can also create some predictions about the ecological and evolutionary responses of organisms to climate change. And if you want to do that first, you can use also principles from evolutionary biology, and you can just go to the literature and you will see that there are at least three ways in which natural populations can respond to a major threat. One is they can fly, they can fight, or they can die. Basically, they can fight through migration. So organisms can move to other places. They can fight through acclimation or adaptation, or they can be local extinct. Migration is probably a good way to escape for environmental stress, but the thing is that if you start talking or thinking about ocean warming and ocean acidification, you will see that these are global scale stressors. So the thing is that where to migrate if everything is changing. So migration is probably not the best response in the long term. And in some cases, some populations that they are living in environments that are highly variable. In some cases, they can live even under conditions that are extreme, even beyond those that are projected for the end of the century. So the question is, okay, are they already adapted to these conditions that we predict? So forget about migration in this case. Let's talk about phenotypic plasticity. And we have been during the whole morning talking about that, and we know that phenotypic plasticity allows organisms and populations to adjust fitness and performance, basically increasing the tolerances with the thermal performance curve as an example, and like a buying time in some case to cope with these environmental changes. But the thing is that plasticity can be even more than that. It can even go beyond buying time to cope with environmental variability. And this is a work that we developed with some colleagues in Australia, cows in the Middle East, basically looking at how plasticity could be also important in terms of sexual selection, also in terms of the changes in the species distribution. And for instance, with Jenny Donaldson, we described how using plasticity, you can involve that in terms of different models about species distribution models, and you can predict, especially at the edges of the species, how depending on the amount of plasticity, some species can just go beyond or contract the distribution in the face of climate change. But the problem with plasticity, and it's probably like that's the dark side of plasticity, is that if you continue increasing the change or enhancing the change of the environment, then there are some limits for plasticity, and there is going to be a mitigation, but beyond some limits of this, and if the environment continues changing, plasticity is not enough. Yeah, because basically, and the organisms, the only way that they can cope with these changes are basically through adaptive evolution. And if you remember, adaptive evolution depends in a great extent to the amount of phenotypic variance, but also in the amount of genetic variance. So I will show you a little bit more about that now with some examples here. So we are going to continue talking about the ocean acidification. You will see that there are some regions across the planet where ocean acidification seems to be quite natural, basically because there are natural processes that accelerate the acidification of coastal waters, and then we can ask questions about if these populations are already adapted to these future conditions. So here we are looking basically if the populations are more plastic within upwelling systems, and if there are signals of local adaptation. So basically what I'm going to show you now is like a different test of the climate variability hypothesis about higher tolerances and plasticity in regions that are more variable, and less tolerances, lower tolerances in regions that tend to be more stable. And I love scissions, and this is an example now from, forget about coronary bacteria, phytoplankton. We're going to talk about scissions, and here you have an evolutionary framework You have two species, one that you know that is Loxichinus albus here in Chile, that is closely related to the Antarctic sea urchin Sterochinus, and one sea urchin that is in California, that Eugenio said this morning, that is the red sea urchin Mesocentrotus franciscanus. But this one is quite distant in terms of the evolutionary history. But if you look at the ecology, you will see that Mesocentrotus and Loxichinus, they live in two very variable and highly variable environments, upwelling systems. And Sterochinus lives in a very stable condition, that is Antarctica. So closely related, but in very different environments, distantly related, and very similar environments. So if you just look at the single responses of ocean acidification, we can see that it really affects the early ontogenetic stages of these guys, basically by affecting body size, delaying the growth of the larvae, and also by affecting the physiological rates, like the respiration in this case. You will see, for instance, increasing the pH increases the metabolic demand of the organisms. And the worst case scenario is usually connected to increases in temperature and decreases in the pH. So higher metabolic rates on these kind of stressful conditions. And even looking at the gene expression, we can see also how all of these changes in basically here, what I just want to highlight is all of these changes in temperature and pH influence mainly energetic costs, like especially the use of ATP and the transformation of ATP in different other functions. So we can infer that ocean acidification and ocean warming induce energetic costs for these organisms. If they want to be tolerant to these conditions, they need to change the amount of energy that is allocated to different functions. And that develops in the long term some trade-off. So more energy for tolerance, for survival, is going to decrease the energy for growth or for reproduction and so on. And this concept is quite important in evolutionary biology and should be also quite important in climate change biology. But I said, we need to forget about the idea of using a species as a model of study for climate change biology, and we need to start thinking about more like the diversity that we have in terms of populations and phenotypic variation. So what about the responses of these different populations? So go back to California, from the south, close to Santa Barbara, to the north, you will see strong variability in PCO2 pH. And basically, the north tends to be more variable, with the upwelling is stronger, and the south of the upwelling here is like weaker in some cases. If you go to Chile and the upwelling system here along the coast of Chile, you will see a strong influence from the fjords and strong variability here induced by the upwelling here. But you are more probably experts than me in this case, but it's also like a highly variable conditions, especially in the upwelling system. If you go to Antarctica, you can also see strong stability, especially at the south of the Antarctic Peninsula, and higher variability in temperature and PCO2 pH in the north of the Antarctic Peninsula. So we have, within species, we have environments that tend to be more stable, environments that are more variable. And therefore, we can create some kind of environmental stress line with these regions that are outside of the upwelling or at the south of the Antarctic Peninsula that are more stable, and regions that are more stressful or variable that are at the north of the Antarctic Peninsula or within the upwelling system. And therefore, we can create some hypotheses about the capacity of being plastic for these organisms. So here we're looking at a similar index that you mentioned, like the percentage of change in body length for the larvae. And here you have decline, high environments, high variability, low variability or stress, and the three different species. In black, the one in California; in gray, light, the one here in Chile; and the dark gray, the one in Antarctica. And this is, like I said, changes in body length, the effect of ocean acidification in the body length of the larvae. One of the things that you will see is that the effect is lower in environments that are more variable. Yes, so they are more tolerant in terms of the morphology in these environments, and environments that are more stable, they are more affected in terms of the morphology. So you can see kind of like a clinal response in the two species. Also, if you compare in terms of the highly variable upwellings and more stable Antarctica, you will see that the response is higher, the effect is higher in Antarctica, basically because it's more stable environment compared to the upwelling systems in California and Chile. That's from the point of view of morphology. But I said this is highly connected also to the energy, the way that they use ATP and transform and allocate the energy to different functions. So here you will see metabolic rates, respiration, and you will see an opposite trend. Here, environments that are more tolerant in terms of the morphology, they used to exhibit higher metabolic rates. They need more energy to cope with that tolerance. That means that there is a trade-off there. So basically, compared to more stable conditions. So these are affected in the morphology, but they don't spend that much energy compared to these ones that are more tolerant in this sense. So basically, those things are trying to support the idea of the climate variability hypothesis. We will see also that it's not only for temperature, but it can also be applied to ocean acidification as well. But in general, what I really want to highlight is that the context-dependent effects of environmental variability plays an important role in terms of the adaptive potential and the capacity for being plastic in marine organisms. So we really need to consider this fine-scale resolution of variability across the species distribution. And the next question is probably for a different talk, but I just want to highlight this for the future, and how this variability influences the adaptive evolution. We're talking about plasticity, but how this plasticity and the variability of the environment influence the evolutionary potential of the organisms. So just as a conclusion here, I just want to highlight here also that natural populations are context dependent, so they are really influenced by the local conditions. They tend to be locally adapted if they are isolated from other populations. So each population can exhibit different physiological plasticity, different tolerances and sensitivities. Some populations can cope with environmental variability through phenotypic plasticity, but other populations can cope with that through phenotypic and molecular adaptations and also local adaptations. So this is just an example, and what I want to do now is, sorry for the, but I just want to highlight, I hate to make like a self-promotion, but I want to highlight here, we have a special issue on phenotypic plasticity in Philosophical Transactions Week. It was from this year, sorry, but it's free available, and we are trying to look at the effect or the importance of considering phenotypic plasticity, not just in changing oceans, but in changing environments at all. We can see how phenotypic plasticity could be target of natural selection. We can see in that special issue how phenotypic plasticity is important for considering species distribution. We can see how phenotypic plasticity is also important for understanding cryptic phenotypic diversity. In some cases, you can have an idea of the phenotypic diversity in a moment, but under stress, that phenotypic diversity can increase thanks to phenotypic plasticity and so on. So I really suggest you or recommend you to go there and try to have a look to this really cool special issue. And the second thing is that my lab started like last year at the Hong Kong University, and we try to understand mechanisms of phenotypic and molecular adaptation to environmental change. I'm looking for postdocs, PhD students, master students that want to look at this kind of integration, so not just from phenotypic plasticity, but also environmental physiology, population genetics, host microbiome interactions, and so on. So if you want to look at that, if you want to do an internship in HKU, or if you just want to do your PhD or postdoc, just send an email or get in contact with me, and we'll be happy to host you. So thank you, Cristian, for the invitation. I feel at home because I love Chile. I lived here for 8 years, so it's super cool here. And thanks to all the institutions and people supporting all of this research. Thank you, guys.
So I have time for questions.
Pueden ser en español.
Puede ser en español, sí. Si quieren preguntar en español, háganlo.
So the Antarctic urchin was like had a range of response very large compared to the temperature, right? But in my mind, at least, the Antarctic population, they always seem to be very homogeneous. I guess they are not.
Yeah, for this one, no. So it seems, no, so Antarctica is quite huge. And the whole Antarctic Peninsula is also very extreme. And the variability in environmental conditions, is, especially in the Antarctica and the peninsula, is huge. So if the north of the Antarctica, like Escudero, that area, it can go from just rock to full color of ice in just a few months. Yeah. And if you go down to McMurdo, to the US base, or Adelaide Bay, you will see that it's very constant in these conditions. But the way that the environment is connected, the populations are connected, are also affected by the biogeography of these conditions. So in some cases, there are connectivity between populations, but other populations seems to be isolated from those, especially in the constant conditions. So I have this is still work in progress, but we have an idea that is, even in some cases, despite of gene flow, like the homogenization of the populations, we can get divergence in phenotypic plasticity due to local conditions. And I have this with the searches as well as with the limpets, and we are looking at the phenotypic physiology, but also gene expression, and we can get this kind of divergence across the Antarctic Peninsula. So it seems to be a trend. But the thing in Antarctica is that organisms tend to be like a very, Antarctica is quite stable in overall, and the organisms tend to be like a low tolerance to any change. So if you increase 2 degrees Celsius, they die. If you change a little bit the pH, they are completely affected. But some organisms like this one, like Sterocynus and also Nacella, the limpet, they seems to be some of the few organisms that are plastic, but not as plastic as those in temperate regions.
So your plasticity metric was standard, right?
Yeah, exactly. So it's like a percentage of
so exaggerated.
Yeah, exactly. So
I have a question. Yes, I was talking with, for instance, with a journalist. You know, like he was asking me about the main objective of the symposium. So I was talking about the plasticity, the organisms that are plastic, you know. So it gives the impression, you know, for some people when you say that, you know, we say that there are organisms that are plastic, they can deal in some way, you know, with the release of carbon dioxide to the atmosphere, the ocean acidification, or the increasing of the temperature in the ocean. So my question is, this is the message in terms of the cost, you know, and the limit of the plasticity, okay, especially in systems, you know, like a very, you know, corrosive or very, you know, stressful, like upwelling regions or the coast of Chile. I mean, which is the message that we can say in terms of the plasticity, you know, for stakeholders, for people that are trying to connect this kind of science, you know, with the decisions.
Well, that's probably super difficult.
Yeah.
I guess one of the things that I always like to say is we need to forget about the winners and losers idea. So we always say, okay, these are the winners and these are the losers, and I think that is kind of like a mosaic of responses for the species. Some of them, there could be some local extinctions, yes, that's true. But there could be also like other populations that keep the species present across the distribution. So that's one of the things. But the other thing is that we need to consider plasticity and the potential for evolution, especially if we want to manage aquaculture, or like in the case of the sea urchins. I have another work with these ones looking at the adaptive potential and the genetic variability. And even those populations in the upwelling at the north that are highly tolerant and they cope really good with the environmental fluctuations there, the genetic diversity is reduced basically because fisheries and like the exploitation is huge. So if we start also looking at ocean warming, human pressure, and all of those things, and even removing species that are important for this one, like seagrasses, seaweeds, and so on, we can expect like an enhanced effect of climate change and anthropogenic effects. So I would say that if you want to develop like a conservation strategies or management programs for resources, you need to use this kind of ideas of plasticity, differences in plasticity, and also differences in potential for evolution. But it's quite hard because usually stakeholders, they don't think about that, or it's hard to transmit. Some is probably great for later on. But the other thing is like we can say, okay, everything is plasticity, like a change is plastic. And in some cases, and you're going to talk about that, it's not like that. Like not all the changes are adaptive. Let's say that. But yeah, sorry, I'm not brave enough to.
I just want to put, you know, the discussion about the application of plasticity for stakeholders.
Yeah, at some point we need to make this transition in terms of like the basic science and try to use more this science in terms of knowledge exchange with the stakeholders and also with the government, especially to get the idea of using like the whole species distribution to get an idea of the potential for management. So. Thanks.
Rodrigo, I was thinking in this field of data concept that we start to see that the subtropical or tropical waters are going up more often than used to. And we used to have more migration, for example. But you have a species that can be plastic. They get evolution, but you finally going to have some competition for the area. When you
Competition?
competition by the because you have a southern different species.
Yeah. So
Migration to the north. I
So-
was talking about what you
yeah. So there is this paper in Science from Greta Peck and the team in Australia, and they're exactly looking at this because the environment is changing. There are some species that, let's say, they are more plastic because they are more tolerant to these changes. Yes. So they can cope with this and they can colonize new environments. But that's not the only thing. So they need to be also good for competition, and they also need to be good for species interaction, basically, because not only competition, they are going to get new food sources, new kind of environments, and so on. So I would say that it's like an integration of plasticity and also ecologically relevant ideas about species interactions to get like a better prediction of the changes in the species distribution. So competition for sure is one, but other things like facilitation and even predation could be one of the good ones for determining how a species can cope with these changes in the species distribution. Yeah, even in some cases, like competition could be a good factor for expanding population range.
Any other question?
Okay.
Okay, thank you. So the last speaker for this morning is Sandufon. Sandufon is a researcher from the Göteborg University in Sweden.
Great. So I'm very sorry to be the guy between you and lunch. I will try to keep you awake till then, and please don't leave yet. And I would say it's going to be really hard to talk after the last great two talks we had, and I will try to, give a different perspective now on some of the concepts. And actually, I would like to start before I start my talk to talk a little bit about what you guys just talked about, and like how do you want to communicate the concept of plasticity to stakeholders? And my answer to that would be maybe we don't have to. I'm actually reading this book now that on science communication by Randy Olson, and it's like, don't be such a scientist. And the idea is that why do we do these things? And we do it for two reasons. One, because it's science and it's exciting, and we want to understand how evolution works, and the second part is because we work for society. And what we need to do is basically provide tools for these deciders to basically take decisions to, save the planet, like decrease carbon dioxide emission, change our behavior, and so on. And for sure, plasticity is a key concept that we need if we want to upscale from monitoring that is done everywhere now and better done, and provide these solutions. And maybe that's what you want to communicate. It's not, you don't need to communicate that to everybody. You need to communicate that to people who gives money to scientists. Because it's like, that's important. That's what we need to understand. If you really want to achieve to the tools that are needed by society, we need to understand this. And there's a lot of really cool basic scientific questions that we can answer to this. So I think that would be my answer to that. And so what I will try to talk about is about the fact that, as has been said, like not all plasticity is adaptive. Not all plasticity is good. And sometimes it's very complex. And I will show you an example here where actually we show that it can be good for certain things and bad for some others, and it's all about trade-off. And I just will try to put a few concepts. This is a really good paper if you want to start reading about this. And I don't know if the presentation will be available, but if you want a copy for the reference, let me know. So that's kind of a good paper on phenotypic plasticity, how that can contribute to evolution in different ways. Is it like hiding evolution, like limiting evolution, or favor, like something that can favor it? So it's a good start if you want to read about these things. And I will also present a lot about sea urchins. So that's the hero of the day. We had 3 talks that talked about sea urchin. And there's a reason why there are so many people working with them. It's a great scientific model. So it's ecologically and economically important. You have a century of data already available. If you go into the literature, you're going to see they have a lot of really cool data already available. So you can really start building hypotheses. If you want to test something, it's a great model. You have a genome available, so it's great if you want to do genomics and so on. A lot of functional tools. And also, it's sensitive to different stressors and really, really plastic. So if you want to study plasticity, that's a fantastic model. And the villain of the day is acidification, right? So there's the hero and the villain. And I put a few slides to remind a little bit what acidification is, but I don't think I need to do this. It's been done really well. But it's directly related to CO2 carbon dioxide emission, and basically we have a change in the carbonate chemistry. It's something that we observe. We saw a lot of data everywhere around the world, so the pH goes down, CO2 goes up, and so on. And we know for sure that there will be consequences, right? We should try to summarize a little bit what is known. Half of the tested species so far showed a negative response. The other half, like no response or positive response. And again, what we need to understand today is what this consequence will be depending on different scenarios of what we will do. And it can lead to really dramatic effects. And that's just one example from my lab like a long time ago, where we exposed eggs from these guys, so brittle stars, another echinoderm, to different pH scenario, and basically just decreasing the pH by 0.2 pH unit was enough to kill them all. So we exposed the larvae. This is how they look like after 5 days, like a beautiful larvae with a nice skeleton. And if you decrease by 0.2 pH unit, they form a blob like that and they all die. And it's quite different from what you've seen with sea urchins, where they can cope with larger differences. And the reason is with what has been shown also before, is that the larvae never experience a pH lower than 8, ever, right? So they live in a really, really stable and high pH. So they are adapted to these conditions, and a small change basically killed them all. And that's something that is so really important for society, is the fact that it's already happening. So you heard about the story probably about the oyster farmer on the west coast of the US who had trouble to produce a little spat for the aquaculture, and it's happening in other parts of the world now. And that was caused by acidification. So we have a stressor that is strong, can have really dramatic impact, like basically species disappearing within a few decades and impacting businesses. And the question of the day is like, what is the contribution of phenotypic plasticity in responding to this stressor? And we know the answer is yes, through the talk we had this morning. But what I wanted to show is like a couple of examples of how phenotypic plasticity can play a role. And just exactly what has been said more or less all of the talk, the idea of phenotypic plasticity is that we have a genotype, different types of environment, and at the end you have different phenotypes. And these sea urchins have been studied really extensively for this, and in particular for their response to food. So the job of a sea urchin larvae is to eat at the beginning. So they are in the water and they eat, and if they are not successful with that, they're going to die and fail in producing a juvenile. And so if there is a lot of food in the water, what they will do is keep their arm, the little rods they have, short, because it's very easy to capture enough food. But if there is not enough food, they will invest some of their energy in having longer rods because they are more efficient to capture food, right? So they can really change easily their phenotype. And it's really amazing because if you change the food concentration around them, they will shift between phenotypes really, really quickly. Okay, so they are really, that's a really great model to study these kind of things. And one of the questions is like, why would the species be plastic? And the answer is quite obvious, is because we want to be able to cope with a wider range of environment. But that can only happen if you have several rules. One of the rules is that you have to be exposed in a variable environment. What's the point of being plastic if we live in a really like constant conditions? But really importantly, the variability has to be predictable. So you have to be sure that the variability will be, the same more or less every year. If you have something that happens only once in a while, you can't really be prepared for that. And then also selection should favor different phenotypes. So if you have one phenotype that will work in all the environment, there is no point of being plastic. You can just have, several phenotypes will perform differently. So one phenotype will be better than the other, like the food stuff I just showed. The long arm phenotype is better in low food conditions. So it's kind of interesting to try to be plastic to do this. So you should not have one phenotype that's better in all of the environment. So the second question was like, why not everybody is plastic? Because that seems kind of a really cool trait to have. And it's because there is a cost to it. And again, we had some nice example of this today. And just to illustrate that, the cost of plasticity, I will show you an experiment we've done. So what we did is we took a bunch of sea urchins, so that's the green sea urchins that is collected in Scandinavia, and we basically spawn, make small larvae, and then for the first part of the experiment, we put them under two different conditions. Either like constant, so no variation in pH, or fluctuating pH. And we made like some kind of stressing conditions, so you have mortality and selection happening. And then at the half of the experiment, what we did is some of them, we kept them in the same conditions, so constant all the time, or fluctuating all the time, or constant all the time here. And then for some of them, we just transferred. So they were selected at the beginning in fluctuating, and then we transfer into constant, or the other way around. And then we checked how they were behaving, and we checked fitness. Do they survive, yes or no, basically. And this is what you see. So this is the mortality rates, and that's a different condition. And you can see that if they are kept in fluctuating all their life, or in constant all their life, stable, similar kind of mortality. So you don't see a difference in performance. But then if you take them from stable environments, so they are selected to be living in stable, and transfer them in fluctuating, the mortality double. So they don't like to change from constant to fluctuating, which kind of makes sense. You expect that if they said they are selected to have one that cope with really constant, they won't behave really well in fluctuating. But you have also the other way around. If you select them in fluctuating, they actually don't like constant anymore. They don't perform as good in constant conditions. And that's kind of the cost of plasticity. So that explains why not all species are plastic. But then there's, of course, also, so because of this, between species that live in different environments, you're going to have selection for plastic versus non-plastic, and we had an example of that from population comparison. And I will show you an example from one trait, which is the pH regulation of the stomach. So feeding is extremely important for these guys. I explained that, with the size of the arm, but they also need to digest the food really efficiently. And they use enzymes that have a really narrow pH range. So they are really efficient in a narrow pH. So in the stomach, if you go and measure it, you're going to see it's alkaline. So the pH is around 9 in these guys. And if you change the pH outside, what can happen is that the pH will change inside the stomach, and then the enzymes are less efficient. So they decrease their efficiency by 20%. But what is really remarkable is that these tiny little larvae that are 1/10 of a millimeter are able to compensate for that. So they have this ability to control the pH inside the stomach using pumps, proton pumps mostly. But then it's interesting to see that if you take different species of these larvae, not all of them will have the same ability to compensate. And that will lead to more or less variability, plasticity in their stomach ability to compensate for pH. So this is measurement of the pH inside the stomach of a wide range of uterostomes. And basically, the more variability you have, the less capacity they have to compensate for pH, because that's what happens when you expose them to a new pH environment. All right, so you can see that some species like that one or that one are really good at keeping the pH right, whatever the condition, right? But some others, like the Californian urchins that Eugenio was studying, you can see they have a wide variation in the pH of the stomach. So they have much more variability, more plasticity. And then if you try to plot this variability on this axis and see how much that affects the mortality if you expose them to acidification, you can see that the ones that are actually really good at, actually at keeping the pH right are actually much more sensitive, because there is a cost for that, because you have to invest energy to keep your pH right, and then if you're too stressed, you can't cope with the cost anymore and you die. So you have a really nice relationship between these two. And interestingly, all the species that are here, that are actually really good at surviving, live in variable environment, when the other ones are living in constant. So you had a strong selection between species in developing this ability of coping with, controlling the pH inside the stomach or not. So just to show that it's genetically determined. So in summary, so far, plasticity is genetically determined, so your ability to be plastic is related to your genome. There is a cost associated to plasticity, so not all species will be plastic. And then plasticity can be selected and lead to local adaptation. All right? So for the second part, I will discuss more about that, the fact that plasticity can be good or bad, adaptive or non-adaptive, right? And if you want to represent that like theoretically, you have two different environments with two different adaptations, two different types of genome, and two different phenotypes. So this phenotype is the optimal phenotype in that environment, and then we have another one that is here optimal in that environment. You can see this one is bigger than that one, for example. So plasticity will be like if you transfer that one into that environment, you're going to have a reaction norm, and that's going to lead to this. Or this if you transfer this one into that environment. And then you have a plasticity that is adaptive because the new phenotype goes closer to the optimal, right? But then in some cases, you have that. Let's say that you have two different environments, two different genotypes, leading to the same phenotype. And then if you transfer that one here, it's going to go here. And if you go transfer that one there, it's going to go there. So basically, you deviate from the optimum. So in that case, it's a bad idea because you deviate from the optimum, so it's non-adaptive. All right? People still following? All right, good. So I will show you an example of these, like some example of adaptive and non-adaptive plasticity. And again, sea urchin larvae. So as Juan Diego just explained really clearly, if you expose them to low pH, you have always this delay in development. So they take more time to do the same thing. And that's linked to energy. So they need more energy to compensate for the cost of being in a more stressing environment. They have less energy available for growth, so they grow a little bit slower. And that's what you can see here. This is the larvae that is 3 weeks old, grown in pH 8.1. This is how they look like at 7.9, so they are smaller. They have a different morphology, so the size of the arms are a little bit more robust sometimes. And then you have the one at 7.7, even smaller. And you can see this is what is called a rudiment. So that's basically what will create the juvenile layer. It's much bigger here, it's smaller here, and not even there yet. So you have this delay of several days, right? And then we have to consider that. So is it good or bad? That's kind of the question we're going to try to answer for the second part of the talk. And to answer that, you really have to consider the species in the context of the natural environment, not only in the lab where you measure the change. And there is a nice quote from David Attenborough that is in a presentation of the new show that is on Netflix, and he said, Darwin revealed that all species have evolved over time to best exploit the condition in which they live. He further realized that these conditions are not simply those of geography and climate, but also their relationship to other lives they live alongside. So we have to consider the change we see in the context of ecological interactions. Okay, that's extremely important. So we have this that I just mentioned. So they grow slower, and that's another way of showing it. So you have the size, you have the time, and you can see this is the control, the high pH, this is the low pH. So it takes them 2-3 extra days to reach settlement, right? And my question to you is that, is it good or is it bad? And I'm going to make a vote to keep you awake. So who think it's a good thing that they're actually smaller and delaying their development when they're exposed to low pH? Good guys, you lift your hand. But then your thing is good. 2, 3, okay. 4, 5, 6, 7. Okay. Who thinks it's bad now? 1, 2, 3, 4, 5, 5. So it's a bit more good than bad. Okay. We'll see. Before we go really to answering this question, we explore the answer, we have to remember why larvae exist to start with. So the job of a larvae is to produce a juvenile. So you have the adults living on the benthos, they release eggs and sperm, they fertilize, produce a larvae that would be in the plankton for a certain amount of time, and then they settle and produce a juvenile, and the juvenile will mature into an adult. So that's the cycle. So the job of the larvae here is first to survive, 2, to accumulate energy, so they eat, and they need to accumulate enough energy to physically produce a juvenile, and then swim around to find the right place to settle, right? And it's really important that they find the right spot. Because if you produce a super good juvenile that is in the wrong place, they're just going to die because of starvation, because of exposure to predator, and so on. Oops.
Touch the...
Yeah, here we are. So the first thing is that they need to survive. So every day they spend in the plankton, they are exposed to predation, right? And it's huge. So it's been estimated that around 15% of all the larvae die every day because of predation. So you can estimate the cost of spending 2 extra days in the plankton by doing a little bit of simplified modeling. So here you have the effect size on growth rate. So that would be the control. And that would be if you grow faster, and that would be if you grow slower, right? And then this is the impact on survival. And basically what's happening is that the slower you grow, so the more extra time you spend in the plankton, how much it leads to a cost in survival. And to read this is the kind of effect you observed in the green sea urchin, so they grow slower by about 1/3 sometimes, and that leads to an increased mortality. So there's like 90% more mortality in the worst case scenario, just by spending these few extra days in the plankton. So that's a huge bad thing, right? Having they spend more time in the plankton, they were more exposed to predators, so they're going to be less of them reaching settlement. So first part of this, bad. Okay, so the guy is voting bad, 1.3. The second part is they need to eat. That's extremely important. If they don't have food, they won't gather enough energy, and sometimes they will expand their time in the plankton for several months, because they will stay in the plankton and keep eating, and sometimes they starve to death too. But then, if you see this effect in the lab, so you see like that they grow a little bit slower, and you check their performance for feeding, they feed more or less the same in principle if you keep them alone with plenty of food. But in the real world, they will have to compete. They will have to compete with other larvae, like other species and so on. And the question is like, how will they perform if you put them in that context of competition? And then we organized with a course last year in June, an experiment to test that in the lab. So we wanted to see, we have two different phenotypes, right? The low pH and the high pH. So we know what they eat, it's more or less similar if they are separated, but what happens if you put them together? Which one will win? Is there a phenotype that is better than the other for feeding? So we wanted to test that hypothesis. So we wanted first expose the larvae to 2 different pH to create these 2 different phenotypes, then put them into competition. Put them in the same jar and see which one is winning. And we wanted to do that where there is plenty of food or when the food is scarce. So there were 3 different phases. The problem is that how do you recognize them? Because I told you like they're really small, 1/10 of a millimeter, right? And sure, there is a difference in phenotype, but it's the same species. So it's kind of hard to make the difference if you take a sample and check under the microscope. So we said we have to find a way to label them, to label like which one is one phenotype, which one is the other. And to do that, we use calcium. So that calcium is a really cool substance that you just put in your culture, and it's labeling the skeleton. So we said if we label half of them, like the high pH phenotype, it will be fluorescent, and the other one won't be. And then through time, we can follow the proportion of the fluorescent and non-fluorescent in the different culture and see which one wins. All right? Still following? Cool. So this is how it looked like. So it was a huge experiment. We had a lot of different cultures. So we had all of these were controlled. So high pH, pH 8.1. This one was pH, I think we used 7.5. And then we labeled half of them with calcium in both conditions. So we could actually test, is there an effect of calcium or not on their growth? So the first part, we just did that, put like 50,000 larvae in every bottle, and keep them happy for 7 days. And we randomized the whole stuff, of course, and then we checked how they were surviving and so on. So for every bottle, we had time, we had the density, and we calculated the mortality rate. And then if you present it, looks like this, where you have the controls and the low pH. And then you can test, is there an effect of calcium or not? Is that having an influence on their survival? Because in theory, in the literature, they say there is no effect, but we wanted to test it. And we tested it, and what we saw is like no effect of calcium, which is really good. That's what we wanted, and an effect of pH. So that's something that has been documented in the literature a lot of times. You have an increase in mortality rate if you expose them to low pH. But that was not really what we wanted to test. The next part was the most exciting, was now we can make competition. So that was designed like this. So we had some bottles, 3, where the larvae were kept in controlled condition or low pH, right? With or without calcium, so we can test the calcium effect again. And then we made also, so some of them were kept in controlled conditions, some of them were kept in low pH, and then we made a mix. So we could control larvae with the low pH larvae, so the 2 different types together, and then let them compete for the food. And again, we made all these crazy combinations. We could be sure, 100% sure, that there was no effect of calcium. And we randomized, and then we had 2 hypotheses. So we could calculate with a single culture, with one phenotype, the mortality rate. So we had the mortality rate for the high pH phenotype, the mortality rate for the low pH phenotype, and then we have two hypotheses. Either these guys compete or not. If they don't compete, that means like they are independent from each other in the jar when they are together, and then the mortality rate we should see for the bottle should be just the average of high and low phenotype. The other situation is that they compete for food, and then what we expect is that there will be an additional effect. So the mortality rate that you observe should be higher than the average. All right? So we tested that, and the first part we put like a lot of food. So in a way, the competition is not really harsh because there is enough food for everybody. And if you do that, what you see is that there is no competition. So you have the mortality in the high pH phenotype, the mortality in the low pH phenotype, the mortality in the bottle where they are together. And then if you compare that to the average of these two, is the same stuff. So in the first case, no competition whatsoever. But the interesting part was the phase 3, where we did the same stuff, but we give them just enough food to be happy. You know, like really limited condition of food. So in that case, competition should be harder. And what we see is that the mortality in the high, when they are together, is much higher than what we expect if you had like the average of these two. So you have an additional cost, an additional mortality when they are together. So that's indicating that there is competition in the model. So that's what we predicted with our model. So what happened is that you have the mortality to the high pH and the mortality to the low pH, and then we check which one of the larvae were dying extra, where the extra cost of mortality that is due to the competition. Was it the low or the high pH phenotype? And we could make the difference by checking which one were labeled with the casein. And what was really cool is that always the low pH phenotype losing the battle. Okay, so we have an additional cost when they are together, so they compete, and the high pH phenotype always wins. So that even if they are in control pH or in low pH, it doesn't matter. It's always the low pH that loses. So that shows that in the lab, when you do like 1 pH at a time and you don't make competition, you don't see much of a difference. But if you're in a real world where competition happens, it's a really strong fitness impact. So again, for the guys voting for bad, this is a bad thing. So first, we have an additional cost due to predation and an additional cost due to food. So why would they do that? Is it just like a side effect of this energetic effect, or could be adaptive for something else? And then there is another thing that we check, is the swimming. Because I told you they have 3 jobs. They have to survive, they have to eat, and they have to find a right spot for settlement. And to study that, we check if the morphology change that you see had an impact on swimming. And if you do that, you can actually film the larvae in an aquarium with a current and see how the larvae behave. And if you do that, you can see that the larvae that have the low pH phenotype swim slower. So they actually change their swimming speed. And they do that so they keep at a certain day, even if they are smaller and have a different phenotype, they have the same swimming speed that they would have in the control. So they basically swim a little bit slower because with time they swim faster and faster and faster because they get bigger. But then they don't really have similar kind of effect in the low pH. So basically they swim a little bit slower. I'm going to ask you again, is it good or is it bad to swim slower? I like that. You look like whatever. It's bad? Bad? Okay, it's bad. Let's check. So we did some modeling to actually test this. So we have models where you can model dispersion, and we tested different scenarios. What if they swim like this, they swim like that, they have a delay or not? And this is kind of the cartoon version of this. But what happened is, in the control, they produce, so the adult produce a larvae that will swim for 26 days and then find the right place to settle. So if you have a delay in development, as I told you, what happened if they keep the same swimming speed is that they're going to swim for longer, like let's say 3 extra days, and the risk is that they're going to go too far and miss the ground where they need to settle. If they grow slower, what's happening is actually they change the speed, and despite the fact that they're going to swim for longer, they're going to still arrive at the same place. So in that case, I'm going to guess that this is a simplified version, but we checked like how much larvae were lost or not, depending on different scenario. And it seems that this is a purely adaptive thing. So they changed their morphology to compensate for this delay in development. And at the end, they arrive in the right place. So in that case, this is good. So I asked you at the beginning, is it good or bad? Actually, it's both, right? And if you check for the different parameters, it's bad for survival, it's bad for eating, but it's good for finding the right settlement ground. And that's a really, really important of their life, because if they miss the ground, all the rest is done for nothing. So it's about trade-offs. That's what you have to remember. But that's really important to interpret the change we see in the lab in the context of these complex ecological interactions and behavior. So to summarize, I said that plasticity is determined genetically. There is a cost associated to it. Plasticity can be selective and lead to local adaptation, and it can be adaptive and non-adaptive in the real world. And that leads to complex trade-offs, right? And I think I'm going to finish with a quote from Shakespeare, since I started with a bad joke about Shakespeare at the beginning. So there is nothing either good or bad, just thinking makes it so. So thank you.
Thank you, Sam. So, time for question, please. Eugenio,
you talk about the control of pH in the larval stage that has a cost of plasticity. Do you think that that particular trait could be like a different cost in a different time of the life cycle, like say after metamorphosis or early?
Absolutely. I guess the bigger they are, the more costly it's going to be. And I just showed that for the stomach, but it's also true for the cellular, the cells inside. For all the PMC around the skeleton, these cells also control really tightly the pH. And the bigger the skeleton, the more of these cells, so the higher the cost. So I'm pretty sure that it will be stage related. Yes.
Yes, show us it's larger the structure of the zero central is low pH, and they those speed because are heavy or the gas alone provided is low speed.
So the change in speed, you mean? It's they change their morphology. So it's biomechanics. So they change the size of their arms, and also they are more robust. So it's just the physical appearance that makes actually the speed difference. It's not like the ciliates movement or anything like that. It's more like their morphology. So they adapt their morphology to reduce a little bit their speed. Smart, huh?
Yes. Yeah. How do you measure the pH inside the lab?
Absolutely. Yeah, that was. I had a super talented postdoc. So we had this idea, like how because for us it was kind of an obvious thing, like they have to control the pH inside their body to be able to cope with this. And that's how we kind of struggled, how can we do this? And Maike Stum was in Germany doing a PhD with Frank Melzner. She said, oh, maybe we can try to work with the medical community, and because they have these micro electrodes to measure pH. So it was homemade, like micro electrode that allowed to measure in the extracellular fluid, and Maike was amazing. She could enter the stomach of these little things through the mouth without damaging them alive, and put them, and then measuring pH, changing the water around. That was great. But then we had the next level was we wanted to measure it to the cells, and there is no probe that can do that. So for that, we use pH-sensitive dyes that you can just put in the water. It's loaded into the cells, and then it's just like an indicator. Depending on the pH of the water, you have different ratio of fluorescence, and you can measure. And that looks very easy, but both techniques took us more than a year to adapt. But no, it's working really well, and Maike is doing basically continuing to work on this, and she does that in a range of different larvae, and so it's kind of a cool technological development. Yeah. Yes.
Yeah. Sorry, I think maybe I missed this part. Sure. Could you clarify if those differences in swimming speed refer to horizontal speed or vertical?
We check both actually. So Karen Chan, who did the work with, so she's an expert on these things. So we check different parameters. I think it was vertical, horizontal, and I don't remember which one. I think it was the average speed or something like that was modified. But we had all the data on what kind of the parameters were, like the velocity, the vertical, horizontal, and so on. And honestly, I don't remember. It's been years, and I didn't read the paper recently. But she had this nice system to track them, in 3D in the water, and we did it with or without current. So we have the data, but I don't remember. That's my honest answer.
I voted for bad, and I still think that the third item is still, it's also bad.
It's also bad. Why is that? No, because we basically put that in a model, right? So we had this. She had this SRing model where you have all the currents and so on, and we simulate different scenarios, like same speed or speed that is, like delaying development or not, and you have much less loss of larvae if you have that behavior that she incorporates in the model. Yes.
But then when you said you have a picture, when they are at pH 7.7, that the rudiment is smaller.
Yes.
And even if they reach the right spot at 26 days.
No, they're going to reach it at 29, which is the point.
Because
they
they
are
reach at
delayed,
29,
right?
the rudiment is going to be
exactly.
competent and ready to learn.
Yeah.
Okay.
And we have beautiful, really beautiful juvenile at low pH. I think they can make it, it just takes extra time.
Any other question? Do you agree that this kind of information can be used, for instance, for aquaculture, for instance, by, I don't know, like manipulating, exposing organisms to fluctuation conditions to try to reduce, mortality? I'm thinking about the application of this kind of approaches, for instance, for the mussel aquaculture in southern part of Chile, where you have a very heterogeneous environment, with corrosive water and very stressful conditions, a lot of fluctuations, and the other more, stable environments.
Yeah, we talked about that, right? That actually maybe conditioning the adults to a certain type of condition can make the larval stages more resilient. And there are some evidence of this like carryover effects or transformational effect, like that instead of taking the adults out and immediately produce the larvae, you keep them in the lab in fluctuating maybe or low pH conditions for a certain time, and then do.
But do you know any experience, in the industry that is already applying that kind of approach?
I don't know if they do it in the industry, but I know Laura Parker made some work on that where they pre-expose the adults for a few months, and then actually I was making the larvae more resilient. So yeah, I think it seems to have some preliminary data. Maybe you have more? Or?
Yeah, no, I'm thinking next to that, that I hate the assisted evolution idea. Yeah. But in some way, in aquaculture, it's like that. You are just selecting some particular genotypes or phenotypes that are highly tolerant. That are not affected.
Fast growing.
Exactly. But should we focus on selecting that or just selecting more plastic individuals?
Yeah, but that's the thing, is that it's also like what you said in many of your papers, is that it's most of the time they select for one trait, and that makes them much more sensitive to other traits. So in a way, it's what you want to select for. Like, it's always a risk. If you put all your eggs into one stuff, it's a risk. So but I think that might be a good thing to test. Is like try to keep them in fluctuating conditions, select for more plastic maybe individuals, and see if it's good or bad. And I think we might have some surprises.
Yeah. Cool. Last question, okay.
Yeah, well, my question, thanks for the talk. So my question is about the experiment you made with the fluctuation conditions. And I was surprised because even if they are estimated to the fluctuating condition, when it changed to the stable condition, to the constant, you still have high mortality rates. So one would expect that if the conditions are better, they would adjust the expression of the genes or whatever. So why do you think this happens, or did you measure something? Because if this is, you attributed that to the plasticity cost, right? The cost of plasticity. So, but if they don't need to use those attributes, why do you still have that cost?
I didn't measure. I think that the good way of answering that question would have been to check that the genetic, and we didn't. I think I will repeat that and try to do that, because we put the condition we put was stressing. Yeah. So the idea was to kill half of them over the last 2 weeks, to have a strong selection. And we had a lot of genetic diversity to start with, because we put a lot of eggs and sperm from different females and males. So the idea was to really have a strong selective pressure and select plastic genotype and non-plastic genotype. So after that, you can't really go back because you had a selection process. But I can't prove it. It's just like a hint now. But I guess that the mistake we did was not to check. And next time, I think it's easy to do. It's not a complicated experiment. So we can repeat this and test it, to see if we have a selection or not. If not, that's a little bit more intriguing, I agree. But you can have fixation also at some point. But come and work with us.
Come on. Okay, any other question? Because we have an interview with a journalist, and I don't know now that we have to forget to talk about plasticity.
No, we will.
Okay.
Even Christian for
Thank you very much. Finally, I want to thank you very much to all the speakers, and thank you very much for coming and participating in this very interesting symposium. Thank you.